For section 4, we're going to move into what we call one-sided limits. We've been talking about regular limits, now we have these one-sided limits. And we also have to discuss continuity when we're talking about those. So the reason we bring in one-sided limits is actually because of continuity. Okay, 3 conditions that reveal a discontinuity at some value of x is equal to c, some number. If the function is not defined at x equals c, so that could be, like I don't really have room here, but hopefully you guys will in your notes. If we have some function that's doing something like this, and then we have a hole, function's not defined there, making it discontinuous. That would be 1. We also could have, we've kind of talked about something like this, maybe a vertical asymptote, like so. Function that does something like that. But there's also this other one here, due to the function going imaginary. We have some functions that we've worked with over the course of your careers in math. The square root functions would be 1. So it starts here, and then it continues this way forever. That's some sort of square root function, let's say. All right. The function stops because it actually goes imaginary at that point. So that's a discontinuity as well. There's a break in the graph. Okay, so vertical asymptote I kind of already talked about right there. Sorry, I got ahead of myself. There's a break in the graph, like with the step function. Step function, if you remember, it looks kind of like this. Something like that. So breaks in the graph. We've talked about, let me see if I'm getting ahead of myself again. No, it doesn't look like it. We've talked about piecewise functions. So if I have something that does this, a break in the graph there could be a discontinuity. Piecewise functions don't have to be discontinuous, but they a lot of times are. This last one, number 3, is kind of an important one. The limit of the function exists at x equals c, but it's not equal to the function at c. And we've had a couple of those on the homework. That's if I have a function that does maybe this. There's a hole there and it continues. So the limit does exist, but the function itself maybe has it drops down and is specifically that number at that particular point where we're taking the limit, where we have the discontinuity. So that reveals a discontinuity as well. If none of these things happens, then the function is continuous. Okay, we have 2 different types of discontinuities, removable and non-removable. We've been working with removable mostly in the last couple of sections. We just didn't really talk about it as being removable. A removable discontinuity. Some other function can replace the original function exactly, except for the original function has the discontinuity. The new function does not. That's what we call a removable discontinuity. They can be removed. Those discontinuities can be removed by creating fancy ones and using the dividing out or rationalizing techniques. So that was what we were doing in the last section. Holes are removable discontinuities. The limit at these discontinuities exists. For non-removable discontinuities, there is no function that can replace the original such that you remove the discontinuity that you're talking about. These discontinuities cannot be removed using our techniques. In other words, we can't do anything with it. These are the breaks that we're talking about. So like vertical asymptotes, piecewise functions possibly. The limit at these discontinuities does not exist. So I'm just going to put a little sketch here for the removable discontinuity. We might have something that looks like that. That'd be a parabola. You'd probably see some sort of rational function with some sort of factor in the denominator that would cause division by 0 right here, but you could divide it out. we might have, well, since that happened, I guess I'll just do this. With a vertical asymptote here, maybe that happens. Can't do anything with that. Some piecewise function, just like the example on the previous page, non-removable discontinuity there also. Okay, to determine the type of discontinuity, follow this algorithm. So these are the steps that you should follow, something that you should just know, have it memorized or something. It's not that I want you to memorize an algorithm to solve all the problems, but this is the idea that we follow when we're presented with problems like this. So first, determine where the discontinuities occur. They occur when you have division by zero, usually. If you have a piecewise function or some other type of function, maybe there's some other situation going on there. But for the most part, you're looking for division by zero. Plug in the value of the discontinuity into the original equation. You'll have to do this for every discontinuity you found. So if you found 6 discontinuities, you're going to have to plug all 6 of those in, because some might be removable, some might not be removable. If you get 0 over 0, the discontinuity is removable, like we learned in the last section, which means that there's a hole. So 0 over 0, we have a hole in the function at that corresponding x value. So we could find the limit there. If you get a number divided by 0, so like 1 over 0, or 5 over 0, or some other number divided by 0, then the discontinuity is non-removable, which means there's a break in the function. It's probably a vertical asymptote, unless you have a piecewise defined function, and then it's just a break. But usually we're going to be dealing with vertical asymptotes at that corresponding x value. So let's take a look at these 4 examples that we have here. F of x equals 1 over x. We need to analyze this and see if there's going to be any discontinuities, and then determine what type of discontinuity it will be. So for f of x equals 1 over x, what do we do first? So we decided that 0 is where we're going to have a discontinuity, right? Because that results in division by 0. So then what do we do? We need to check it to see what kind of discontinuity it is. So what do? Plug in the 0. I get 1 over 0. So therefore, this is a non-removable and what type of discontinuity does that look like if we were to graph it probably? We actually know this because we've done this one before. Vertical asymptote. So that's the idea on these types of problems. So for the second one, f of x equals x squared minus 1 over x minus 1, what do we do first? Look for division by 0. Do we have division by 0 here? If x is 1, then there's division by 0, right? So we're going to plug 1 in to the top and the bottom and see what we wind up with. We have 1 squared minus 1, which is 0. 1 minus 1, which is 0. We get 0 over 0 here, which tells us what? It's a removable discontinuity. Removable discontinuity at x equals 1, which means it's a, what type of discontinuity? It's a hole. And what would we do? Divide out. Good. So we have a hole, and we could simplify this down to find the limit at x equals 1 by using the dividing out. The dividing out technique. Okay, the third one, y equals sine x. What do we do? what's the first thing you do? Okay, what do we need to plug in here to get a discontinuity? Huh. Why? Okay. Can you expand on that a little bit? Why? Because it's continuous. This is a continuous function. So there is no discontinuity here. This thing is continuous. Don't make something happen here just because we are finding limits of as we approach discontinuities. It's a continuous function. Remember your first step. Determine where the discontinuities occur. Okay, last one. G of x equals, looks like we have a piecewise function here. Sometimes we have like a squiggly bracket like that. Sometimes we don't. It doesn't matter. We have a piecewise defined function here. What should we do? Okay, so where would the discontinuities occur? Does it depend on which function we're using? Are we using both anyway? I mean, if this is the function, then we're using the whole thing at some point. Is it continuous? Are guessing games allowed in calculus? No. We have to have a reason. So just say it's continuous or just say it's discontinuous. We better figure it out for sure. How could we figure it out for sure? Graph it? Well, that's better than just guessing, right? Okay, so we graph it. Not right now. I don't have a graph up here. I don't want to graph it. Yeah, so? I mean, just as an example, what if I graph this thing and then x equals 0, like my first function maybe does that, and my second function does that. Is this a continuous function? No. But what if my second function did that? Is this a continuous function? Yes. So we need to figure out what this thing is doing, but I don't want to use a graph. I want to use algebra. So what can we do? That's a pretty good idea. What number should we plug in? Why? Yeah. But doesn't this piece exist here? Won't -1 exist there? Okay. Is this piece continuous? On its own, this function right here is continuous, right? On its own, is this function continuous? So where are we concerned? We're concerned at 0. Because either we're going to have a break or we're not going to have a break, right? Everywhere else the function is continuous. So we need to evaluate both pieces at 0. If we get the same number, then the function is continuous. If we don't, then it's not. All right? So if I plug 0 into the top, I get what? 1. If I plug 0 into the bottom, I get 1. Is the function continuous? Yes. That's right. You need to think a little bit on some of these problems. Same exact functions. Now we're going to graph them. So we have f of x equals 1 over x. We've done this one before, right? We've seen this one before. Do we know what it looks like? We don't need to use a calculator here, probably. I don't know what foof means. What should I probably put on here first? I don't need a scale. Vertical asymptote goes through. All right. Got a vertical asymptote there. And now, does this function look like this? Or is it like this? This one? Okay. So it does this? I'll take your word for it. Okay, so we have a non-removable discontinuity here in the form of a vertical asymptote. Second one, x squared minus 1 divided by x minus 1. We said that we can create a brand new function for this thing by using the dividing out technique. We know that we're going to have a discontinuity at x can't be what? Okay, so we have a whole at x is not at x is equal to 1. Which means that this thing, by the way, up top, if I have a discontinuity at the bottom and I'm using the dividing out technique and I have some sort of factor down here, guess what I'm going to wind up with up top? X minus 1 somehow, okay? So in this case, you can kind of simplify the problem in your mind as you're working on it by knowing that I'm going to have to wind up with x minus 1 to divide out. So the top factors into... Okay, so now we divide out the x minus 1s, and we have what as a function? Like x plus, so the f of x equals x plus 1, which is a what when we graph it? It's a line. Would you have graphed a line if you were asked to graph this thing? Probably not. But if you graphed it on your calculator, you would see the line x plus 1. So we have plus 1 here, and then a slope of 1. So I'm just going to put a bunch of dots on here so I get a nice accurate line. I know that I have a hole at x equals 1, so right here I'm putting my hole, and I continue. And then I draw on my line. There you go. Okay, the third one, y equals sine x. We know what sine x looks like. It is a continuous function. Don't make it more difficult than it is. Yes, I do have one of the special limits. The limit as x goes to 0 of sine x divided by x is 1. But that's not what we were looking at here. We're looking at just sine x, which is a continuous function. We know sine starts at 0. It goes up to 1. I'm going to make my scale a little bit different here. 1, 2, 3. Maybe I'll go up to here. And 1, 2, 3, 4. So I know that my function does something to this effect. Right? That's terrible, but you get the idea. We know what sine looks like. Okay, the last one. This is the one that had the most confusion for you guys earlier. This is how you graph a piecewise function. It's just a little review of what we did in Algebra 1 and Algebra 2. Take the first piece, g of x equals x plus 1, and graph it. Okay, x plus 1 is a y-intercept there, and I'm just going to put a bunch of dots for my slope all the way through. Once I've done that, then I'm going to actually fill in where this thing lives. It lives when x is less than or equal to 0. So that is, here's x is 0. Less than or equal to 0 is this way. I don't know why that happened. Less than or equal to 0 is this way. So, or equal to, that means when x is 0, I go up to my function, and it actually does exist there. And then less than means I'm going to graph every value this way. I don't need these dots. You can erase them or leave them there. I don't really care. They're just there to help you place that function. Now we go on to the second piece, and just for greater effect, I'm going to change colors. G of x equals x squared plus 1. We know that that's going to look like what? A parabola that was, use vocab. So translated, up 1. So we have a vertex here. Technically, the function does not exist on this piece, but that would be an open circle on an already closed circle. We know that the function is continuous from the last problem. So then we go over 1, up 1, over 2, up 1, 2, 3, 4, over 3, up 9. That's way off the graph. So now we're going to graph our second piece, and that's the graph of that piecewise defined function. No break there, so the function is continuous. There is more going on there calculus-wise, but that won't be We won't talk about that for a while yet. The next thing in this section is what we call one-sided limits. So sometimes we're only interested in the limit of a function as it approaches some discontinuity from one side, from only one direction. If we're looking at the function as it approaches some value c, then the notation as we approach from the positive, the right side, so let me put a little graph on here, I got a function, and as I approach, maybe a discontinuity right there, from the right, that is considered from the positive side. Even if we're on the negative side of the graph, that is from the positive side, the right side. The notation is the limit as x approaches that number with a plus sign, kind of like in the exponent of that function. And that just means as you approach from the positive side only. Likewise, from the left side would be from the negative side. So now as I approach from over here, that would be like potentially coming in from negative infinity, so that's why it's called the negative side. Same notation, just with a negative sign in what would be that exponent for the number. Most of the time we're only going to see this when we're dealing with functions that stop, that suddenly end is how I put it. So like square root functions or broken functions, like piecewise functions, something like that. That's when you're going to start to see these one-sided limits that we're talking about here. So for these functions, the limit otherwise would not exist because if I have a square root function, if I'm talking about the limit here, it doesn't exist since there are no values over here and this side is approaching some number here. So we don't get the same number on both sides. However, if we talk about the limit as we approach this value right here from the positive side, now we can talk about the limit of that function. Same thing is true for your piecewise or step functions or something like that. We can talk about the limit as we approach from the negative side. We can talk about the limit as we approach from the positive side. Okay, for example, find the limit as x approaches negative 2, and the plus sign means from the positive side. That is the function. It's a circle. It's a half circle. It's a Searle C, yeah. Okay, so as we approach negative 2, here's negative 2. So as x approaches negative 2 from the positive side, so that means I'm moving this way towards negative 2. What is the function appearing to do as we approach? It's going to 0, yeah. So the limit as x approaches negative 2 from the positive side of the square root of 4 minus x squared. Can I direct substitute here? Yeah? If I plug negative 2 in, I get 4. 4 minus 4 is 0. Square root of 0 is 0. So yeah, I can direct substitute. It's just that the notation is telling me that I can only go from one side. Okay, so the limit in this case, we will call 0. Normally, the regular limit, without that plus sign right there, doesn't exist. Okay? Same thing is true if we go the other way. The limit here would also be 0 as we're approaching from the negative side. Okay, so that's all I wanted to say there, I guess. Okay, a little note about intervals here. That's kind of the same function that we were just looking at. I like to use interval notation. I think the book likes to use interval notation as much as possible. And remember, interval notation deals with parentheses and brackets. In this case, we would be using brackets because the function does exist at negative 2. The function does exist at positive 2. So those points actually are there, which means that we do have a solid ending point for that function. So the interval for the x values would be negative 2 to positive 2, surrounded by brackets. And that's kind of what I have there. An open interval we might look at would be starting at 0 and then going off to positive infinity for f of x equals the square root of x. That graph starts at 0, 0, and then goes forever in the positive direction. So that is a solid starting and then a infinite ending. And infinity is never enclosed by a bracket. So this is domain. Range in this problem would be the y values that are getting graphed. 0 actually did get graphed, right, twice, but it did get graphed. And it goes all the way up to positive 2. If you plug in 0 in that function, you would get positive 2 as a result. 4 minus 0 is 4, square root of that is 2. So the range of that guy would be bracket 0 to 2. Okay? The range of this guy would be bracket 0 to parentheses infinity. Bracket means it's there. You can get there. Okay, it's solid. Parentheses means you can't get there. Inclusive, yeah. We have a little calculus concept here, finally. Getting into some calculus. This is what I would call a logical concept, the intermediate value theorem. In this class, we're going to learn lots and lots of theorems. You do need to know the name of the theorem. There's no special theorem number or anything like that. Know the names. And then learn the language of calculus too. This is written in the language of calculus. You're going to see this a lot. All that says is you have a continuous function over some interval. Doesn't matter what the interval is, but it's a closed interval. So you see those brackets. And you also have the function at one end is not equal to the function at the other end. Okay? Here's our interval, a to b. The function at a, at one endpoint, is not equal to the other function, or the other endpoint of the function. Okay, and then we have this value k. K is just any number between f of a and f of b. So any number between f of a and f of b means we are looking at what values? The x values or the y values? Am I looking on the x-axis or y-axis here? Y-axis. And k is any number between the function at a and the function at b. Then there is at least one number c, some different number c, over the interval from a to b. So now if we're looking at a number over the interval from a to b, are we looking at the x-axis or y-axis? X-axis. So there's at least one number c over the interval from a to b such that the function at c is equal to this number k that we said was between f of a and f of b. So what the heck does this mean? The language of calculus here is going to be confusing to you guys until you get better at it. Once you learn how to read this, you should be able to form a picture fairly easily. For now, you don't know how to read it really, so the picture to form is kind of mysterious. I'm going to draw a graph, and I'm just going to put some random function on here. I like drawing parabolas, so I'll put a parabola on here. Okay, now f is a continuous function. We have a continuous function on the closed interval a to b. So I'm going to make some sort of closed interval here. Let me change colors, and I'll put a right here, and I'll put b right here. Okay? It's continuous over that interval, right? Here's a up to the function, so this would be f at a, and then b is down here, so this would be f at b. And in between, the function is continuous. That's this part right here. F at a is not equal to f at b. F at a is up here, f at b is down here. So we've completed all of this up to here. Okay? Now, k is any number between f at a and f at b. So that means between f of a, which is here, and f of b, which is here, k can be anywhere in this range right here. Okay? Then there is at least one number c, some other number c, in the interval a to b. So the interval from a to b, let me pick a different color, how about green? The interval from a to b is here. So I'm picking some number in this interval right here. And this says there's at least one number c in the interval from a to b such that the function at c is equal to k. All right? So let me pick out a k here, just for example. Let's make k right there. The function at k is over here. So this would be f at k. You guys agree? Okay. So now all this says is I can pick some number c on my interval from a to b such that f at c is equal to k. Well, where would c have to be in order for that to be true? Which axis am I looking at? The x-axis. F at k is here, which means my c must be right there in this case. Okay? That's all this thing is saying. As long as I have this set up true, some interval a to b, the function is continuous such that f at a is not equal to f at b, then there must be some value, c, such that c is equal to a specific number between f at a and f at b. Okay? Basically, all this says is the function is continuous, and I can find any number I want, f at k, as long as you're on a closed interval. Yeah. Yes, that's why I said it's a logical concept. All right? Is it way more complicated than it needs to be? Probably. But you have to learn how to write this and read it in the language of calculus. Okay? This covers everything. It's logical to us, yes, but this covers every possible function we could ever talk about. Even functions you've never even heard of before. This one covers them all. As long as the function is continuous, you can find any value you want over that interval between the function's value at the endpoints of that interval. A good example of how to use the intermediate value theorem is in a problem like this. Show that the polynomial, here's my polynomial, has a 0 in the interval 0 to 1. And we're going to use the intermediate value theorem. Again, the intermediate value theorem really is just logic. Don't get bogged down by the language. Understand what it's trying to tell you. That's the key to this theorem and every other theorem, and really calculus as a whole. Understand what it's telling you, not the language that they're using. Okay, I don't even need to graph this thing because I'm using the intermediate value theorem. The intermediate value theorem tells me I need my interval, which in this case is 0 to 1. I need, so this is A, and this is B. I need f at A. I need f at B. So what am I going to do? So f at A will be f at 0. So I get 0 plus 0 minus 1, which is negative 1. F at B will be f at 1, and I get 1 plus 2 minus 1 equals 2. Okay, so can I use the intermediate value theorem here? Is the function continuous? Yes, it's a polynomial. So the function's continuous over some interval from a to b. The other part is f at a and f at b can't be the same thing. Are they the same thing? No. All right, so we have different numbers here. We are looking for a 0. So using the intermediate value theorem, what can we logically say? So the intermediate value theorem says if I want a specific number over the interval that's between f at a and f at b, I can get it, right? What specific number are we looking for here? We're specifically looking for 0. Is that number between f at a and f at b? Yes, which means that I can find a 0 between 0 and 1. So k in this case would be equal to 0, yeah. Has a 0 means k equals 0 is what we're trying to find. Okay? What value of c is it? I don't know. But it's between 0 and 1 for sure, because I just proved that using my intermediate value theorem. So, show that the polynomial has a 0 in the interval 0 to 1. Show it. That means I got to show this, and then I got to state why it's now true. Okay? So I would write some sort of sentence that says, and hopefully a well-written sentence, that says something to the effect of, what? We're looking for, like, I'm not going to write the full sentence, but basically looking for k equals 0, because I have 0, right? Which is between f at 0 and f at 1. Therefore, that's the symbol for therefore. Therefore, I'm not going to go total notation on you and give you a backwards capital E, but I'm not going to do that. Therefore, what? We're looking for k equals 0, which is between the two endpoints. Therefore, there is a 0. You could say there exists a 0 between. In the interval would be a little bit more formal than between.
You don't have to find C.
You don't. It doesn't say. Use the intermediate value theorem to show that there's a 0. It doesn't say find the 0. It says show that there's a 0. So that's all you have to do here. But this statement right here has to be there. You have to show that you understand what the intermediate value theorem just told you. Okay? That's the work that has to happen here.